Hi, I wanted to make this short note to talk about one of the web warm-up questions from earlier this week. This one about degrees of freedom of the weather vane shown here in the picture. So what we were tasked with figuring out was how many degrees of freedom do I need to specify the location and motion of the tip of one of the wings of this weather vane. To help us reason this out, I think it's helpful to imagine looking at first a top-down view. And so we would have something schematically like this. Here's the body of the bird, and it's rotating around a vertical axis, right? And then, of course, there are some wings that are attached to the body, around some axis like this. But the whole body of the bird is allowed to rotate around this axis, so it can rotate like this. And we might specify the position of the body of the bird as some sort of angle, right, like this, from some axis direction called the x-axis. And basically what this angle is telling you is which direction is the weather vane pointing, north, south, east, southwest, so forth. And then if we look at a side view, we would have something that looks like this. So somehow I have to draw this bird body. I'm afraid it's going to look like a fish. All right. So there's the body of the bird, which is, of course, free to rotate on that vertical axis. But then attached to the body are the wings, which look something like this. And they are free to rotate around this horizontal axis. So the wings can rotate like this. And again, we could imagine measuring those the position of those wings with some angle. Let's call it phi, right? So that angle phi would tell you where are the wings in this vertical plane, and then the angle theta would tell you where the whole bird's body is in the horizontal plane. And so there are 2 degrees of freedom here, 2 variables to specify the position of the tip of one of those wings. Now notice that that's a little bit strange because in the Cartesian coordinate system, right, we would need to specify the x, y, and z coordinate of any object, right? But so if we wanted to specify the unique position of the tip of the wing, we could set up some sort of 3-dimensional coordinate system and then give you 3 coordinates to say where that wing is, right? So that would be 3 variables. But what we're claiming here is that we only need to have actually 2 variables to specify the position of the wing. And the reason for that issue is that there's a constraint going on here. The wingtip is constrained by the length of the wing, and the position of the body is constrained by this axis that it can rotate through. So although the object is moving in 3-dimensional space, because of those constraints, we only actually need to have 2 variables to describe it. And so that's something that's going to come up fairly often in Chapter 7 when you're doing these example problems, is that although we'll have motion in 3-dimensional space, quite often you'll find that you can describe that motion with fewer variables, which is what this whole process is about, is trying to identify what is the smallest number of variables that I need to actually specify the position. And then, of course, those are the variables that we'll use to calculate our Lagrangian. So the fewer we have of them, the better. All right. So I hope that helps you understand a little bit about degrees of freedom in systems, and will help you to tackle the degrees of freedom activity worksheet.